In this example, we're going to be solving the linear differential equation x dy over dx equals x squared plus y, given the initial conditions y1 equals 3, using the integrating factor technique. So we're first going to start by getting this differential equation into what's called standard form. We'll do this by first subtracting y from both sides. Next, we're going to divide by the leading coefficient. The leading coefficient in this case is going to be x. It's what's right there in front of the dy dx. And we're going to be left with dy over dx minus 1 over xy equals x. Now that our equation is in standard form, we're going to be finding the integrating factor. The integrating factor is represented using the Greek mu sub x. And this is going to be equal to e to the power of the integral of whatever is right here in front of our y value. In this case, it's going to be negative 1 over x dx. So I'm going to factor out the negative here. So we're left with mu equals e to the power of negative integral 1 over x dx. I'm going to rewrite this as x to the negative 1 dx. Solving for this integral, we get mu equals e to the power of negative ln x. At this point, we don't need to worry about adding a c value, or that we don't need to worry about adding a c to this integral. E to the power of negative ln x can be rewritten simply as 1 over x. So mu sub x equals 1 over x. This is going to be our integrating factor. Next, what we're going to do is multiply both sides of the differential equation by mu sub x. So what we have there is we have 1 over x times dy dx minus 1x y equals x times 1 over x. Factoring that out, we have 1 over x dy dx minus 1 over x squared y equals 1. This is kind of where the magic happens in these kind of differential equations. What we're left with is basically the product rule. So first, second, second, first. Again, we have f here, g prime plus f prime times g equals 1. This is really important because what this allows us to do is rewrite the differential equation as d over dx times 1 over x times y equals 1. So now that we've completed this step, what we're going to do is we're going to go ahead and integrate both sides. Integrating for the left side, we have the integral of d over dx times 1 over xy equals the integral of 1 dx. So the d over dx and the integral here on the left side are just going to go ahead and cancel out. And on the right side, when we take the integral for 1, we're just going to be left with x plus c. So we have 1 over xy equals x plus c. We're going to multiply both sides by x so that we can get y on its own on the left side. We're going to have y equals x squared plus c times x. Now, since we're given initial conditions in this problem, remember that's that y1 equals 3, we're going to go ahead and plug those into the equation to solve for c. So we're going to plug in the 3 for y and the x for 1. We have 3 equals 1 squared plus c times 1. It's going to be the same as 3 equals 1 plus c, or c equals 2. Now that we have c, we're just going to plug that back into the equation that we got the step before. And our final answer is going to be y equals x squared plus 2x.